I will begin here. Hey, it is 3:01 p.m. Eastern Standard Time. If you're in the Pacific time, though, it is noon for you. We're going to get through this in 1 hour so you can get back to work. So enjoy your lunch if you're eating while you watch. I'm Dave Hobbs, Senior Tech Trainer for Delphi uh, Division of FINIA. FINIA is the newest name of Delco Remy and Delphi Aftermarket and Delphi Diesel Systems. It's offspring of the old Borg Warner, and that symbol looks like a fuel injector spray because that's what it is. And that's PHI is the last three letters of Delphi. That's the old stock market abbreviation. And NI is another language for a beautiful new beginning. So let's begin this webinar on part one. And I imagine some of the techs are holding off for part two because it seems really neat. It's going to be more on the lines of heat pumps and things for thermal management of EVs, but we will get into a little bit of that topic this afternoon with electrically heated thermostats, electric water pumps, and some other things that are unique with hybrids, including some old parts. If you're an old tech like me, and you've seen these like in the 70s, uh, things in the exhaust system to heat things up. Well, some of that stuff's coming back, and just forewarning you, that stuff is problematic. Anytime you put something in your exhaust system that has uh, either a nylon or rubber or any kind of a hose, in this case coolant with heater hoses, or in my day when I was a young tech, a vacuum hose was bad enough, and a valve, a mechanical valve. We're going to use the same mechanical valve technology uh, with some heat exchangers on some of the latest hybrids. These are not plug-in hybrids. These are not EVs. These are just hybrids. All right. So gas and electric combination, like a Prius, only in this case, a Ford Explorer. So more about that. We get into this. We're going to get into heated thermostats first and go from there. So let's go ahead and get to our first slide in order here. We're going to do this next hour. We're going to get you up to date on cooling systems for both conventional and some of the hybrid stuff out there. The hows and whys of electronically heated, aka mapped, as in software mapping thermostats. We'll have a real world case study on a vehicle you might see in your bay anytime, and that's a little Ecotech GM 2.4 in I think it was a 2012 Equinox, and it was set in a P0128 that was not there before the technician worked on it. So I got involved with it. It was a really good technician and a really good case study. I think we're all going to get something out of. And then our second to last point, the whys and hows of active cooling systems. These are what they're calling the vehicles with electric water pumps, not just auxiliary electric water pumps, but the water pump is electric. And then, of course, some scan tool PIDs and tools and so forth that you might come in handy working on today's cooling systems. All right, so let's start out with a couple of pictures of what the heck happened to the thermostat. It looks like some kind of an alien beast here. We're seeing the dual thermostats, a lot of heavy duty applications, and some of the diesels, light duty truck diesels. We're seeing electric stats where we heat the stat, and we also put a coolant sensor into the same body. And we're seeing those plastic housings starting to get brittle and crack. And now the new rage, if you can see my camera here, I'll hold that up real close there. Aluminum, everything going to the potted aluminum stuff. Anyways, that's a bit of a trend change. Of course, we'll see the pitting come back like we have for years with the acidic nature of coolant. So more on that as we get into map stats and hardware of cooling systems. So here's on the right, kind of a cutaway. This has been out there for years. I think this is Mala's drawing. And they actually bought some of our compressor line years ago, air conditioning, because, the Delphi thermal systems, the old Harrison radiator division that made compressors back in the heydays of a much larger Delphi, part of General Motors originally. Anyways, so Mala is the ones that have some of this stuff now. They've kind of taken up the reins. And they've got heated stats. And what we're doing here is we're still running coolant up against this little bulb full of a wax material, and that wax is going to expand, same as always. But we can heat the wax up a little quicker with a little heater element, and it's several ohms. It will obviously be a little less current than what Ohm's law would tell you. I just measured one, this actual one in my hand here that I held up. I measured it earlier today. It was like 16 ohms. So you do the math. If it was just let's say we're really close to the high 14s on voltage, um, that's going to be a little bit less than 1 amp. However, it will probably go down even further, as most heating elements are like light bulbs. They're what's called non-ohmic resistances. In other words, they don't necessarily follow Ohm's law exactly. As the heat builds up in either a light bulb or a heater element, the resistance goes up. Therefore, the current goes down. But it's enough current to heat that wax in there. And actually, as you can see in this graph on the left, we're at 230 degrees Fahrenheit. And we all know that water boils, just water at atmospheric pressure at sea level boils at 212 or 100 degrees Celsius if you're in the metric. All right. But we're not using regular water, number one, and we're not keeping the pressure of the water and coolant mixture, the antifreeze added in, at sea level at 14.7 psi or 100 kilopascals. We're allowing the pressure to build up as the heat makes it expand, courtesy of a pressure cap, a radiator cap, as we've called it forever. And those have been around, keeping pressure in the cooling system since before the days of the electric starter that the founder of the Dayton Electric Laboratory Company, DELCO, the predecessor of Delphi as we know it today, Boss Kettering with his electric starter, they've been keeping pressure on radiator caps since those days, but we can cranked engines. So it's just a known fact. You can lower or raise the boiling point and get that engine to a more optimal efficiency where the air and the fuel mix better, burn more efficiently if you don't keep the engine stone cold. Now, obviously, if it's too hot, then we're going to go the other route. We're going to have all kinds of other emissions and, of course, damage issues. Now, so the map stats, what we're doing is we are then heating the element of that thermostat. In fact, we can actually do the same kind of watchdog on the thermostat performance, and that could be called technically a mapped or a software mapped thermostat, but mainly the ones we call the map stats are the heated ones. And so as you can see, left to right is time on this graph, and up and down is temperature. We're going to bring that from the not boiling because it's under pressure and it's got ethylene glycol as well as water in it. But we're going to bring that temperature down from 230 Fahrenheit down to 176. And that is going to be conducive for a more um, dense air fuel ratio. So you can pack more fuel in because the air is cooler. We're getting more oxygen in that air, and that's great for power. And that needs to happen pretty quick when you put that pedal to the metal and you open that throttle up. So under load is typically when we'll see this happen. So you could, if you want to watch the coolant, the thermostat, actually, if it's a map stat, electrically heated stat, you can actually use your scan tool, watch intake air temp, watch coolant temperature sensor, and watch your engine load and your throttle position. When you get to that spot where you think it's about time for the thermostat to open, now obviously, if you're going to put the vehicle under load, you could do this on a dyno, chain down. You could do it by yourself. Because you're not paying attention to the road on a dyno. But if you're on a real road, which is most of us when we're on a road test, we're paying attention to the road. You're going to have another tech drive or operate the scan tool and you drive, one or the other. Don't try to do both at the same time. All right. Take it from me. You need both hands and both eyes on the wheel and both eyes on the road. So when you're monitoring the scan tool, watching load, throttle position, RPMs, and you're getting to that spot where you think that thermostat should be opening and it does open, then you can actually see how did it respond? Did it open for this 10-second period? And did the temperature drop down? So that's telling you that mapped the electronically heated thermostat is opening. So pretty easy to watch. We'll talk about later how you can actually do some of this on the bench if you've got a hot plate or a stove in the shop somewhere. Don't recommend doing it at home without your better half's permission, but you can test them on a stove or, like I said, a hot plate. Obviously, a microwave ain't going to work because you put metal parts in the microwave. Here's a little bit of information from OBD2 One Stop, and if you click on, that's a free website. Again, I'll repeat it, OBD2, that's easy, and the word one, and then the word stop, actually the number one. So OBD2 um, and the numeral one and the word stop.com, and it'll be all the OEMs will have their little logos there. You're going to click on mechanical, even if it's, computers and PCMs and things like that. Once you click on a car manufacturer, let's say Ford in this case, and then with Ford, you go to the top of the screen and you click on free resources. That's where you'll find things like the owner's manual, which is pretty handy to download a PDF if you're trying to look and see, how do I set this customer's clock because you're doing them a favor of daylight savings time, which was last weekend, or you've had the battery disconnected. You got to reset their clock, and it seems to be a tricky endeavor. That's where you'd find that in the owner's manual. But if you want to see this particular document where I've got a couple of pages of, and it's the tip of the iceberg. I've seen as many as 450 pages in what's called OBD2 theory and operation. Again, you find the FordMotorcraftService.com or the Chrysler Tech Connect or whatever it is you're looking for, factory service information, through OBD2 One Stop. And then if you're in Ford, you click on free resources where you find owner's manuals and you click on OBD2 theory and operation. And that seems pretty lame. I know my OBD2 theory. What are they going to talk about? Code readers and P codes and all that? No, actually, way beyond that. In 400 or 500 pages of documentation, you can download the PDF. For Pete's sakes, don't try to print it, okay? Unless you own a paper mill. But by all means, save it as a PDF on your laptop and or tablet, and then do a control F and type in a word you're looking for, like thermostat. And you'll find everything you ever wanted to know about Ford and how they do their thermostats. In this case, how they do the topic of this field case study, a P0128. So it's a coolant thermostat performance code is basically what it is. The computer says, I don't like the way the cooling system's warming up. It's just something's not going on. It's a 300-second thing. All right. So that's what? Divided by 60 seconds, that's 5 minutes. Now, it gives you some of the parameters, the minimum, the maximum, and so forth. This happens to be for a 2021 Ford Escape, little three banger, and it's relevant through 20 through 23 model year. And the next page in that long document, when we type in, Control F, look for a thermostat, the thermostat monitor, we can see kind of like the engine regulated temperature and then the actual threshold. So black is inferred coolant temperature, a good thermostat. Blue is the actual measured coolant temperature with the ECT, the engine coolant temp sensor. And red is actually what it did here, and it failed. So in this particular period of time, the coolant did not warm up like it should have, and therefore it failed. And so we get an engine that's not overheating. Maybe you're getting some heat out the heater core, out the ducts, and just thinking, what's the deal? Why is it set in the code? Well, the specifications in that PCM is watching that these curves you're looking at right here and seeing that it's just not quite warm enough in the period of time it should have got warm. It got a little bit warmer up here after this period of time that wasn't quick enough. So it's all about the window of those software limits and how the computer sees that as, is this going to be optimal for fuel economy? And most importantly, and probably most relevant, for emissions. So the computer says, nope, I don't think we're going to get the best emissions with this curve that we've seen with coolant temperature warm up. And so it flags the code. Now, in the more modern thermostat applications, we're seeing like a fitting, there's like aluminum gooseneck for the upper radiator hose, and here's the thermostat as integral part of that housing. So it's not just a simple little this part here where my mouse is anymore. So you've seen that for years, but here's what may be a little newer than if you've been paying attention in the last couple of years, we've been seeing an electric stat. So electric heated connector. Typically, it'll be a little different connector than what you're used to seeing because they're also putting ECTs in these housings. So electronic coolant temp sensors will have smaller terminals, obviously, because they're very low current 5-volt ref sensors with, just milliamps of current just to measure what's going on for the ECM's sake, knowing what the coolant temperature is. So we might see an amp or so out of, or even more of this heating action, but we're still going to need to have enough heat with the coolant to make that wax pellet, as I mentioned earlier, to start expanding and allowing that spring to to push out, and or I should say pull up, and cause this valve, basically that's what a thermostat is, to open. Now keep in mind that a lot of thermostats will allow some bypass between the engine and the radiator before the surge tank, whichever the case may be. Um, before the thermostat actually opens. So, and that's so that we can keep some flow of coolant going past the thermostat in order for it to not just be sitting there looking at stagnant coolant. We want a little bit of moving coolant through the system in order to do that. All right, that's the point of the bypass. Now, another thing to keep in mind is you can bench test these. Like I mentioned, here's just a saucepan on the stove. Simple as that. There's a little thermocouple hook right to your meter. So I've got one for my Fluke. And by the way, those thermocouple wires, they are typically kind of tailored to the meter that they came with. So you might keep in mind, when you buy a new meter, maybe it comes with a little flexible thermocouple that you can touch something or put it down into a liquid and, hook it to your meter and then hook your meter into temperature readings. They are typically a match set. So keep that in mind. You might not have accuracy if you took one brand of meters thermocouple wire and put it with another meter. All right. So we're just going to watch as we heat that water up. We're going to watch physically to see if it starts to open, and then also measure at what point it does open with your temp sensor hooked to your meter. Over here on the left, there's a little trivia here. And if you are at a laptop or any kind of tablet and you can hit the chat box, by all means, I'm going to watch the chat box now. Let's see if I can get that up here. I think I've got it up here. Okay. I may just have to have my co-moderator keep an eye on the chat box. I may have had that disappear behind a window on one of my screens here. Anyways, what I want you to answer in the chat box is this question. All right. What is this little thing right here? This little brass looks like almost a little ball, but it actually goes through a hole right here and it's not firmly attached. No, somebody is answering. A bypass valve. Excellent. Thank you. That is correct. And there's actually a nickname for that bypass valve. Now, sometimes it's just a hole. Other times it's got this little brass little thing that wiggles. It's called a jiggle valve. So I think that's just kind of cute humor there. Does your thermostat have a jiggle valve or not? But that's that technical term, Jiggle, jiggle valve. But it's designed to allow air to escape the engine so it can go into the radiator, be burped out or into the surge tank. And therefore, this is why it's relevant. That's why I'm bringing it up. Now, as a young tech, I don't think I knew this. All right. You learn a lot as you get older and you make mistakes wrenching. Okay. So if this is sitting in the engine vertical, like in this picture, it doesn't matter. At least I don't think it does. All right. But if you have it coming in from the side, called horizontal, like in the side of a cylinder head, you want this at 12 o'clock. That makes sense, right? Because, if you've got a system that's not quite totally full everywhere, the air is going to be on the top. And so you're going to want 12 o'clock. You're going to want that jiggle valve or that little bleed hole at the top as well. So just a little simple mechanical tech tip from one wrench to another out there. Okay. All right, let's go ahead and go to our next little topic here. That's the jiggle valve. All right. And have to be in the right direction. Thank you. Exactly. We'll put that in there. So now we have the case study. So we kind of little review of thermostats here, including the new heated stats, MAP stats. And this acronym, I don't think in the first session I gave that acronym definition, but that's something we used in our Tech Assist group years ago. Man, it's a long time, but it's kind of humorous. The W stands for we, like you and me, okay? And then the R is replaced, and the A is all, and the P is parts. We replaced all parts. All right. So that's typically when the tech assist person gets involved. It's like, okay, so the customer, be it do it yourself or even professionals, we just get to the end of the rope and go, we've put about every single part you can think of this car could use in this system, and I'm still got the same problem. We wrapped it. We replaced all parts. So this 2012 Equinox was wrapped. Part of the wrapping, if you will, replacing all parts, was because it has a high miler. And it was a friend of mine who's a master tech, is a very sharp technician. He's always in training classes. That's why I know him. And so he had this, I don't know, 200,000 miles on this Equinox. He'd really got the life out of it, but he wanted more life out of it. He wanted to keep it and keep it going. So he decided to put a water pump in. I don't blame him. I mean, why do you want it to fail? And it picks when you break down. So you put one on first. Wheel bearings are the same way. A lot of parts we do that. And he did the heater core as well. I guess he didn't want to have that leaking down the road. And so, of course, a new pressure cap, radiator hoses. I can't blame him there. And heater hoses, no brainer, right? I'll call it preemptive, not necessarily preventive maintenance like an oil change, but depends on how you look at it. And then hose clamps to go with it, brand new hose clamps and a cooling system, complete flush with a new thermostat, of course, right? Then the post repair additional parts because he now, after doing the preventive maintenance, preemptive repairs, replacing parts that hadn't went bad yet, but probably would because it's a high mile vehicle, no codes before. And we have what we call the Everett Sentia. Here's a new nickname to learn here. Everett, first name, last name Sentia. That's a little pun. Ever since you did all this work on this vehicle, you've got the P0128 thermostat performance DTC. So to address that, my buddy puts in a new coolant sensor. Don't blame him there. And a pigtail harness because we all know how they can leak. And basically coolant can wick its way through the wiring all the way sometimes to the PCM. I've seen in fuel injectors leak and do that same thing. And in the case of coolant, it can be very corrosive to those wires and not very good for the PCM to have a few drops of coolant inside of it. So he put a new pigtail on to prevent that from even going any further. And then a second thermostat. So we have the first replacement, and now we had a second one. All right. Now the question is, was this just cheap parts? Well, in this gentleman's case, he had been a Chevy factory dealer technician for, I don't know, 20 years. And he decided to go off in the independent world and but he still had a good relationship with the parts manager at the Chevy store. So he was getting a really good discount. So that's why he bought all his parts. He knew, it's like money in the bank, factory parts, good stuff, right? Well, in this case, there was one part that maybe the aftermarket might have been better. In fact, definitely was. So more on that when we get into past some of this parameters of what makes up the software mapped thermostat, the P0128. So it's all about the coolant temperature being, below the regulated temperature for a certain period of time. As we go from left to right, some of these, there's the fault code defined as a P0128, gives a monitor description. The monitor is basically just a test. So we'll get into the malfunction criteria. So what the monitor is looking for. And so this is some of the mumbo jumbo that some of these things right down here where my mouse is would be. This would be equated into ones and zeros in software, but it's kind of a description also in English of what's going on. And then the threshold value, secondary parameters, enabling conditions, and time required. And as we look through some of these things, it actually uh, has factors such as ethanol. Now, if this was a flex fuel vehicle, the enabling condition to run this monitor would have this parameter involved. It's got to be E85. It can't be any more than that. So it's less than or equal to 87% ethanol. And that's provided it's a flex fuel vehicle. So, I mean, even the type of fuel will dictate how hot or warm the engine runs. Okay. And then just other factors involved as well, whether going to run the monitor or not. Now, so after my buddy had replaced all these parts for, preventive sake, and then had the new code, this P0128, and then replaced multiple things that had to do with the thermostat, a new thermostat again, and of course, the coolant sensor and a little coolant sensor pigtail. And it still was doing it. That's when I ran into him at a training class in New England. And he asked me, he says, "Hey, you just did a training class on, and it might have been a training class that particular night. We were doing something on programming PCMs. So I was doing a reflash class and I had a reflash tool. I had the J box, universal programmer. I had a laptop, I had a subscription to General Motors. So he asked me if I'd flash his car. For whatever reason, he didn't have that, being an independent, or he didn't have a subscription or whatever. And I said, sure, I'd be glad to do it for you. And so, here's my mentality on reprogramming computers. If it doesn't specifically say to do a reflash, then don't do it. But also, if all else fails, flash. Those two rules are my rules personally. So in other words, it's like being a doctor. Don't do surgery unless it's necessary. Don't just do it because you got an excuse to do it. But at the same time, when all else fails, you're going to the operating room and you're getting surgery because there's risks involved, but you got to outweigh the risks with the benefit. In this case, Mike had seen this. That was my buddy's name. And he said, it says something about increased robustness of the environmental temperature model. Now, that's pretty vague. I mean, environmental temperature model of what? Coolant? I don't know, a transmission fluid temperature. It could be a lot of things. It could be the HVAC, blend door. But this is a PCM reflash. And so it seemed, well, what the heck? If all else fails, nothing else to do, flash. And Lord knows he had replaced everything else. He had wrapped it and then went into the thermostat code parts as well and put more stuff on. So I said, let's flash it. I agree. You got nothing to lose and everything to gain. We did the reflash, seemed to be fine. But within 2 days, the code had came back. So at this point, I kind of felt involved to help him out because, I had done a reflash on his car. So I got on the diagnostic network. Now that's kind of like IATN, actually started by the same gentleman, Scott Brown, out of the Southern California area. And Scott's latest venture is a diagnostic network where you can get onto the internet forum. Technicians can post their problems, pictures, case studies, whatever. So I posted this problem, basically got this Equinox. It's been wrapped. Okay. We replaced all parts and we have the new code now and we replaced more parts and we still have this new code. What do you think it could be? And I had a lot of well-meaning suggestions and answers. And most of them seemed like, well, I think we've already been down those roads. Thank you, thank you, thank you. And then two people out of like 20 responses, so 2 out of 20 texts said, get this particular brand of thermostat. A stant. Now, I'm not here to give a commercial on stants, and Delphi doesn't make these, nor are we a competitor or a supplier or a customer of stant. But I recognize the brand. I've put them on cars for years myself, and I also know this. And here's a little Delphi angle on this. And this is true for a lot of quality aftermarket brands of anything. I don't care if it's a wheel bearing or a fuel pump or an ignition module or ignition coil. There are some times where that particular aftermarket or the factory original equipment part or original equipment service, called OES, as in service, actually does a better job than the one that came with the vehicle, or vice versa. Sometimes the aftermarket that's not even original equipment or original equipment service is not as good as the other brand. In this case, Stant is, I believe, a leading manufacturer of thermostats and a few other things in that realm. And they are OEM and OES. So, that's the part you get the dealership if you're a dealer tech, on a lot of different makes and models. But I believe on this particular vehicle, it was not. It was not the OE or the OE service part. However, it fixed this vehicle. Just like there are some BMWs, for example, and this is official, uh, unofficially, there are some ignition coils that work better if they're the Delphi than the other brand out there that was the factory. In fact, it became official on some models. It's a bragging right that you'll hear me go through sometimes in a training conference, and that is we make great coils, and it's the factory dealer part, OES part, on this model of BMW engine and so forth and so on. So that is just something that's industry wide. If you got a good quality aftermarket part and it's not the official one that car makers using, sometimes it still works better whether it's official or not. And how do you find out which one is the best? Normally, you get the factory part or the OES part, and it's typically will take care of the job, or you find a quality aftermarket part that you have good experience with. But if you're not sure, if you got a weird case like this Equinox, there's where you go to your peers and you find out what they're running into, because nobody has the complete list of every part that's perfect. And it's really all about the software. The OEMs would change the software if it was their part, most likely. Instead of have their vendor go and do a bunch of re-engineering to tweak on the part, they just loosen the calibration a bit and make sure it still meets emissions and does a good job. But sometimes it's just the calibration. It needed a little bit of loosening up, and it doesn't happen. That's why that flash didn't fix this vehicle, and the other brand of thermostat did. Now, thermostats and caps are important. So in this case, we've got a V6. Looks like it's a Cadillac XT5. We're running 20 psi. Back to the basics of caps and stats. 20 psi is a lot higher pressure. That's why that radiator hose feels like a muscle that's all flexed, because it's built up pressure, and that increases the temperature before the coolant begins to boil. That and the addition of, the coolant itself being antifreeze and not just pure water. So 221 degree stat, we're seeing some 230, 235 degree stats. We're seeing 20, 22 psi caps and higher. And here's another little insider thing here. And I'll talk about that coming up. But while that picture's up here, I'll just mention a trend is we're not even threading the coolant sensors in now. On some applications, it's held in with a little fork and a little 10 millimeter or 13 millimeter screw to hold the fork in, the little clamp, and that holds it in place with a rubber O-ring. So the days of everything being threaded. Now, if it's a cylinder head temp sensor, it typically obviously will be threaded in, but if it's in coolant, we may use an O-ring. So that's something. Then there's this, speaking of the devil, there is a cylinder head temp sensor. We're seeing sometimes multiple ECTs and multiple CHTs. So knowing more about that engine temperature, the air temperature, the coolant temperature, the cylinder head temperature gives us more insight into what the combustion chamber temperature is going to be about. And while we're at changing the trends and so forth, we've got solenoids now. They're going to be doing a lot of work controlling the flow of coolant, stopping it, starting it, and auxiliary heaters. I should say auxiliary uh, coolant pumps, water pumps. Now, here in the next minute or so, we'll switch into a new topic of electric water pumps, where it doesn't even use a mechanical belt driven or timing belt driven or timing chain driven water pump. It's using a electric water pump. All right. Before we get to that, um, let's cover a little bit about, oh gosh, we never learn our lessons. Okay. So here is, if you get into exhaust work, you know what I'm talking about. It's dirty, corrosive. I mean, it's just not a good place to put parts that have any kind of elastomers, rubber, hoses, whatever. So this is a case of not a plug-in hybrid, not a battery electric vehicle, a hybrid. This particular hybrid was a Ford Explorer. It just happened to be a police interceptor, and I was doing training for the Los Angeles County Sheriff's Department maintenance garage. And I raised the vehicle thinking, hey, it's just an Explorer, it's just a hybrid. How much different can it be from a Prius or maybe a Honda Insight or something, right? Wrong. It was radically different because the battery pack was lithium ion. It was encased in a really heavy box for obvious reasons under the vehicle. And explorers, whether they be, off-road of a off-road enthusiast or a police officer having to go off-road sometimes to catch the bad guys, got to be pretty well armored up. You don't want the battery pack being smashed around. And because of that, we got to run coolant to the battery pack to maintain its temperature, not too cold and definitely not too hot. And we also want to heat coolant up in order to have good heater performance. So there's a lot of reasons, and especially heat the coolant up for the battery pack in cold climates, because batteries that are helping an engine move the vehicle, hybrid, or moving the vehicle for a short hour, 30 miles, whatever, plug-in hybrid until it becomes a hybrid again, kind of like an EV, or definitely the EVs, the battery electric vehicles. We want those battery packs to be as maintained temperature wise as the people inside the car or the engines themselves. So thermal management is where it's all about. More on that in part two coming up next month of the thermal topic here. But for now, for this month, let's talk about this guy. So in that exhaust system on that Ford Explorer hybrid was this mammoth looking Rube Goldberg monstrosity that had coolant hoses in and out. We're actually flowing the coolant through this heat exchanger. You can see this is kind of covered for protection, but what that's covering is a valve that physically moves in order to regulate whether we're going to heat that coolant up or not with this exhaust gas. Now, if you do exhaust work, this is probably going to be, let's look at the bright side, the cup half full, okay? Service opportunity, all right, to the customer. If it's a LA County Sheriff's Department, I don't think they're probably going to bat an eye. But if it's your customer who's the single, soccer mom or whatever, this is, $1,456 from the auto parts store, your diagnostic labor and your labor to do this work. And this is going to be probably a monster to torch off and so forth. My goodness, why did we do that? Part of my head says that. Other part of my head says, well, you guys got some work to do. Never going to be without work. And I love this old saying. This guy lived 3,000 years ago. All right. Um, and he said he was the king of Israel, ancient Israel, one of the wisest man that ever lived, one of the richest too. All right. Okay. What has been done will be done again. All right. There's nothing new under the sun. Ecclesiastes 1:9. So true today as it was 3,000 years ago when old Saul said that. So this is not quite 3,000 years ago, but it is definitely 40 years ago or more when GM engines, V8s, would close off with something called a heat riser. And techs that are watching right now that are over 40 or 50, you know what I'm talking about. Heat risers would close this flapper right here, and that would allow the one bank of a V8 exhaust system to have to basically back up and go back where it came from, only underneath the carburetor. I'm using some really old words, almost as old Saul. But the carburetors had issues with early fuel evaporation, which was bad for environmental reasons. And so you would warm the bottom of the carburetor up by having a passageway of exhaust gas through a special transfer tube in the intake manifold, which notoriously got carboned up from, the short trip people that create carbon in engines. But if it was all working correctly, we would heat that intake up enough to heat the carburetor up, and now the fuel would not evaporate. It would evaporate more correctly, better fuel volatility, fuel atomization, I should say. $125 back, I don't know, 40 or some years ago. I don't know if that's quite $1,400 today, but there was an elastomer. There was like a silicon coupling for a metal vacuum hose. The metal vacuum hose went to a thermal vacuum switch. When it got cold, that switch would be open, I believe, and that would allow engine vacuum to put this diaphragm in a mode where it shut this, and as soon as the engine got warm, it would open back up and you'd have better exhaust flow. And that's how it worked. Just like I described this, that's how that worked. Heat the coolant up for thermal management of battery packs and the customer in the car, the heater core, so forth. This was doing just the opposite. It was just for the engine's sake, for emissions, but they failed. And they failed miserably. I know I had a vehicle, I owned it. This would rattle, this would get stuck, and I have to put one on about every 2 years. And it was always a big job. So, nothing new under the sun. You folks wrenching on cars today are always going to have plenty to do. You just got to amp up the technology. And remember, it's not really that new of technology. And there's where it goes. Okay, so there's an actual photograph from the Los Angeles County Sheriff's Department maintenance garage. There's the Ford Escape. Um, there's the transmission pan, and what's kind of out of the picture here is a battery pack back behind here, out of camera. But there's the same thing you saw. $1,300, looks like a pre-cat, a post-cat. So the usual stuff is going to be in the way. Big job, going to probably be a failure. I can almost guarantee it. All right. Now, let's do a little trivia here. Talk about just radiator caps, or I should say, in this case, overflow tank, surge tank, whatever you want to call it. This is a reservoir, it's pressurized. And I'll call this cap A, and this is cap B. Somebody tell me in the text box which system cap A and reservoir A goes to. Is this anything to do with the hybrid? Because this is a Sienna, and all Siennas, the minivan Toyota makes since 2021 model year, have been hybrids. Unlike Camrys, which you can get a hybrid or a non-hybrid, Siennas are all hybrids. Priuses, they're kind of like that. Priuses, there's no hybrid or conventional. It's just a hybrid, period. So on this Sienna, which is a hybrid, one of these is the power electronics. That would be the three-phase, two of these, high voltage propulsion motors, motor generators, and then also the inverter and the DC to DC converter. All those items can get too hot, and so we're going to have to cool them down. The other one will be for the engine. So which one's the engine? Good. All right. A, wait a minute. Somebody put A. Let's follow the hoses. Okay. The hoses from reservoir A and cap A go to some kind of electric motor or valve or something right there. Okay. Well, that could be the engine, but let's look to see where B goes. So reservoir B, and that's not even pressurized. That's just like a splash cap, like you'd have on a windshield washer solvent bottle. Let's follow the hose here. Okay, this is the output of it. And boy, that looks like the radiator. So basically, this is a conventional unpressurized reservoir. This is a pressurized reservoir, but it's got a pressure cap on it, and it's going down to cool the power electronics. So A is for the power electronics, the hybrid system. B is for the ICE, the internal combustion engine, right? Now, why does this not pressurize and this is? Well, because it's pressurized over here, okay? Just like old school reservoirs and radiator caps on the radiator. We've also seen two of these, one on each of these. We've seen sealed, one for the engine and one for the power electronics. Now, here's an observation I've made. The one for the power electronics is usually a lower rated pressure cap. It'll usually have a marking on there. Maybe it says 12 psi or 14 or something like that, or 2 psi, whatever. And the one for the engine will be always be higher. You know, it's the 19, the 20, the 21 psi pressure cap. That makes sense. Engines get hotter. Power electronics, you should never start seeing 230 degrees of coolant temperature. You might use the same coolant, but you're not going to send that coolant at 230 degrees throughout that battery pack or throughout that motor generator water jackets, because that would be too hot. They don't even create that kind of heat. There's no fire going on like there is with a combustion engine's, combustion chamber with water jackets around that. So usually the higher pressure cap here on the radiator in this case will be on the engine, and the lower pressure cap will be on the surge tank or reservoir for the power electronics. Now, here's where we get into business, weirdness with business. All right. Sometimes I will see a manufacturer, Stellantis is one of them with the Jeep Grand Cherokees. I've been in a lot. I've had these things tore apart and thousands of miles driven on them for training trips and so forth, scanning them, charging them. They are using a cost savings method of using the same cap on all systems. You think about it, if you get a pressure cap that handles the higher pressure system, the internal combustion engine, would it hurt to have the higher pressure cap on the lower pressure system that never gets that hot? Nope, it would never hurt. So to save money, they just use the same cap. And that's good for the technician. We can't get it wrong that way. But if they were different caps, we would want to make sure we have the higher pressure cap in the place it needs to be. And that's the point I'm making. All right. Now let's go to our next topic. All right. We'll finalize out here mostly with talking about the active cooling systems, what Toyota is calling the D4S engine, which is the latest generation of engines used for, let's say, the Camry hybrid, also the Sienna we're looking at. They're using a water pump that is electric. So it's Ison, that's their pump. This is their picture of the front cover removed. And you can see it's quite sophisticated. There's a lot of, microprocessors and things on board. So, it's not just an electric motor by itself. And I'm going to venture, get out on a limb and say it's a three-phase brushless motor. In fact, I know for a fact it is. However, that's not germane to us like it would be in the same vehicle's fuel pump, which Delphi makes. So we've got fuel pumps out there that are three-phase brushless electric motors. And the wires between the control module that control these electric fuel pumps and the actual fuel pump itself, there's a long distance of all those wires, and we have to know how to do diagnostics on that. And we'll do that in a future Tech Tip Thursday, right? But for now, we're talking about electric water pumps, and these are three-phase brushless pumps, but that doesn't really affect you, and I'll show you why here in a minute. So the idea of these pumps, by the way, is fixes a age-old problem with the same company that was making the mechanical water pump on these little four-cylinder hybrid engines Toyota was using. And it was a weak link. So I owned a Generation 2 Prius, and by golly, it had the same malady that everybody else gets with those pre-electric water pumps where the pump is just small and probably was, never the best design. And the bearing would go out like a lot of water pumps do, right? Belt-driven water pump, bearing starts getting noisy and it starts wiggling, quite a bit of wiggle, and start chewing the belt up until that little belt is almost like a rubber band. It's so chewed up. And you hear this noise, you think your poor Prius motor is about done. And it's really just a water pump. So they put an electric pump on. Great, great improvement. Way to go, Toyota. Way to go, Ison. This is what it looks like. Okay. This is where it mounts and basically, tells you a little bit more about the rotor and the stator and so forth as far as this little cutaway right here. But what really matters is the complexity of the rest of the system. Remember, we were heating those old Corvettes. In my case, I think I had a 75 Pontiac Grand Prix. Oh my gosh. It had a hood as long as a football field, or aircraft carrier, I should say. Anyways, it was a big old car. It had that heat riser. That whole job was to warm up the intake manifold so we had good emissions and good atomization of air. What are we doing here? Number 5, EGR cooler. You all knew about that. What are we doing with coolant over here? We are moving coolant, warm coolant around throttle bodies. We're using the coolant to cool EGR. I mean, the whole point of EGR is to take and displace oxygen in the intake air with exhaust gas, not to heat anything up, but exhaust gas carries very little oxygen. But in the process, we can get things too hot, so we got to cool that down. It's still exhaust gas and it still lacks oxygen. And so it still quenches the combustion, and we don't have the NOx, the oxide of nitrogen, buildup or that pinging noise. But it gets too hot, and you know what happens on diesels? Same thing happens here. We get these things plugged up. So there's going to be service opportunities, lots of hoses. And we'll get into some of the hose works here in a minute. But, obviously an upper hose and a lower hose and an electric water pump and so forth. So this is a lot of hose mapping. No pun intended with the software map thermostats, but you almost need to have a map drawn where all these hoses go. And here is that map. All right. This is from Toyota Service Information. So here's a little 4-cylinder engine. There's a little electric water pump. There's a little unpressurized surge tank, pressure cap on the radiator, showing you the flow, but also showing you these valves here. So these are electric solenoid valves that are going to control the flow of this electric water pump, where the coolant goes and when it goes, in order to do things like cool the transmission cooler, cool the EGR valve, cool the cylinder head, let the engine build up some temperature so that we can build up some heat. Keep in mind, if this engine is in a plug-in hybrid, we'll get more to that in the next month topic, there's going to be some challenges to keeping that engine warm enough. When the engine's not running, we're in that electric drive mode in order, or some other source of heat in order to keep the passengers warm in cold weather, right? So let's look at the pump electrically and talk about how that affects you. Because if you're like me and you got an electric motor, especially a fuel pump, you want to put that amp clamp and hook it to your lab scope and look to see what what kind of a waveform the power to that fuel pump is doing. It's called current ramping. It's like an MRI for the physician to get a really close look and see not necessarily what's happening now with your body, but what could be happening down the road if you don't nip problems in the bud, right? So here we got in the bottom of this water pump, electric water pump subassembly. And up here is the ECM, okay? We got a pair of power wires. So it's drawing some current because there's 2 power wires in parallel. That just makes it less, likely that each terminal is going to toast from drawing too much current. We just split it up amongst 2 terminals for the ground and 2 terminals for the power. Nothing high tech there. The high tech part is these 2 wires here. One is a control, one is a monitor. Very similar to what Ford does with their fuel pumps. They have a fuel pump control module, usually under the seat or someplace like that. If you've worked on a Ford lately, And then you have a regular 2-wire brushed electric fuel pump that is pulsed very quickly by that control module. But there's always 2 wires going to that control module from the PCM. One is to tell the control module what the PCM wants the fuel pump to do, and one for the control module to signal back to the PCM and say, "Aye, aye, Captain, we've carried out your your request." It's called the monitor. So that's what these 2 circuits essentially are doing. Let's look and see what it looks like on a lab scope. So we see a square wave, that would be the control circuit. We see this raw voltage here with the green trace. The red trace is a control circuit, and then the actual current draw, and then the blue trace is another, it's the feedback circuit. And then down here, the little tan trace, that's an amp clamp, inductive amp clamp around the power wire to both power wires to that fuel pump, and it is basically current ramping the condition of the water pump itself. So just like current ramping a fuel pump, very similar. There's my lab scope. All right. And here's Brandon Steckler. He's a little better scope guy than me, and he's able to get some with his math channels and his Pico scope. He's able to see some really good patterns, and this is a known good electric water pump. So he did a Motor Age magazine article on that. Very good article. I encourage you to Google it and read the whole thing. But the point is, you can break into the circuit like you see Brandon's done right here with his amp clamp, and you can look to see that health of that water pump just like you would with a fuel pump. So read the article. Speaking of tools, all right, we're about out of time here. This is some of the tools that you really need today's cooling systems, all right? Combustion fluid. So, we can pull some coolant out and put this combustion sense coolant in the U view and tell if we've got a leaky head gasket or a cracked head. Just a regular old like a battery hygrometer, only this is for coolant, for checking your freeze point. But more superior to that would be the refractometer. Put the coolant underneath this little plastic thing and then look at it through this little scope here. It actually is superior to these in the nature of checking the freeze point of coolant. And then, of course, pressure testing with right here, the caps themselves, and also the radiator or surge tank. Thermometers, whether it be a thermocouple or just in the dash, checking heater performance. And of course, nobody can beat the infrared cameras that will plug into the bottom of your cell phone. I've got mine. It's the top down. I love it. And this is a airlift. Either the airlift, and some manufacturers say use the funnel system, but it's the way to get air out of your system as you put coolant and water mix back in after you do a flush. And of course, if you're a well-heeled shop, you probably have a not refrigerant, a coolant flushing machine like we have here on the far left. So those are some of the tools that you really need to make sure at some point in time you are mastering in your modern day cooling system. So again, hey, we're right at quitting time. I'm willing to hang in there if you've got time. If you've got questions, hit the chat box up. I'm watching the chat box right now. There's the QR code for the same website you went to register for part 1. I'd love to see you all back for part 2. There's my phone number. That's my cell. By all means, hit me with a text first, because I'm probably like you. Don't answer the phone unless you know who it is. All kinds of solicitors these days. And there's my email. So dahobbs@finia.com or 765, that's Indiana, 480-4976. Don't forget to fill out the post-webinar survey. And again, we're going to be doing this part 2, getting into electric compressors and thermal management for hybrids. More on hybrids, plug-in hybrids, especially, and EVs on April the 17th at noon Eastern and Pacific time. All right, that's our next T3. Anybody got a question? I'm here. Otherwise, I will end the broadcast and hopefully see you next month.